All right, here we have 3.2 continued. This is part B, where we are solving systems algebraically with elimination. I will use the word elimination. Your book calls it linear combination. It means the same thing. To use this, our equations need to be in standard form, or our general form, of ax plus by equals c, meaning the x's are aligned on top of each other, the y's are aligned on top of each other, and they equal the constant on the other side of the equation. So make sure the variables are lined up, they're in the same order, and the constants are on the other side, and then we'll be able to use the elimination. So this setup works for elimination, whereas having a letter solved for is better for substitution. All right, to eliminate a variable, we're going to do this by adding the two equations. In order to add the two equations, you may first have to multiply one or both equations by a factor. So we're going to get rid of a letter. That's why it's called the elimination method. And we're going to do this by adding the equations. So we need to make sure that when we add them, we actually can get rid of a letter, so we may have to do some kind of multiplications. So we're going to look at a couple of examples. On the very first one, we have 3x minus y is 13, and we have 2x plus y is negative 8. On the first one, no multiplying is necessary, because the y's, when added, will cancel each other out. A negative 1y and a positive 1y, when put those together, you get 0 y's. So when I put my two equations, I add them together, I get 5x is 5, because 13 minus 8 is 5. 3x plus 2x is 5. The minus y plus y, eliminate. It goes away. And it has to. If you don't eliminate a letter, then you're not doing the elimination method. At this point, I can solve for x. I should easily be able to get x is 1. This is one of my ordered pair. So I have to find the y value of the ordered pair. Well, that requires substituting my solution back into one of the originals. And it makes absolutely zero difference which one you do. I generally pick the first one, but as long as it's an original, it doesn't matter. So I substitute 1 into the x value. I solve it down for y. Once I find that, I need to write my solution as an ordered pair. Always make sure you write your solution as an ordered pair. If you write x equals y equals, it will be marked wrong. It needs to be in the proper form. All right. Here I have 3x minus y is 13, and I have 2x plus 2y is negative 10. In this case, if I were just to combine them, just add them, I would not get rid of a letter. So what I want to do is multiply the first equation by a 2, because I notice that they're already opposite signs, and when I add opposite signs, they go away. But it's easy to multiply a 1 by a 2. But when I multiply, I need to make sure I do it to every piece. Again, when you multiply to eliminate, it needs to go to every piece. So I'm going to multiply the first one by 2. So 3x becomes 6x, negative y becomes negative 2y, 13 becomes 26. I multiplied by the 2. I now get to eliminate the y's. So 8x is 16, solve for x. When I get x is 2, I need to put it back into one of my originals. I cannot put it into this red one. It must go back to an original line. Again, it doesn't matter which one. I'm just going to pick the first one. So when I substitute it back into the first one, 3 times 2 minus y, solve for y, I get negative 7. And there I'm going to write it in proper solution format. Okay, let's look at another one. Let's start with how about there? Here's my two equations in blue. 2x plus 3y is 5 and negative 4x minus 6y is 2. I'm going to choose to multiply by the 2 to the first equation because I recognize right away that it will be a nice easy elimination of my x values anyways. So when I do that, I get a new first equation. The second one stayed the same because I didn't multiply anything to it. When I go and eliminate, I notice I get 0 is 12. Well, just like yesterday with our substitution, whenever we get a false statement, it means that the lines are parallel lines. It means there is no solution, and that can't, and we will never get an intersection point. Okay, so let's try this one. In the blue is my lines here. Here I have to multiply by a 2. If I multiply by a 2 though, notice I don't get rid of anything. They're all the same sign. So then I have to change one of the equations by a negative. Now some of you are like, well, why can't I just multiply by a negative 2 up here? Because when you multiply by a negative 2, 9 times out of 10 you forget to switch the signs to one of your parts. So my recommendation is multiply by the number. Then if you see that you need to multiply by a negative, go through and change all the signs of one of the equations. That way you don't ever have to worry about forgetting to multiply by a negative. So if I multiply by a negative, this is going to cancel, 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 and I get 0 is 0. What that means is that's always true. If it's always true, I get a statement that all reals, they are the exact same line. So with elimination, you're trying to get rid of one letter so you can solve for the other and then substitute it back in. Sometimes they're set up nicely for you. Other times you have to multiply by one equation. Sometimes you have to multiply by two equations. But you always want to set it up so that you can get rid of one of the letters.